Hello everyone. Thanks for watching this video. Next, I will introduce a work, Video Event Restoration, based on keyframes for video anomaly detection. First, let's give a quick overview of the work. To explore a superior approach to modeling normal behavior for video anomaly detection, inspired by video codec theory, in this work, we propose a novel normal behavior modeling paradigm for video anomaly detection that restores video event based on keyframes to detect anomalies. To this end, we propose a novel U-shaped Swin transformer network with dual skip connections called UST&DSC for video event restoration, where a cross-attention and a temporal upsampling residual skip connection are introduced to further assist in restoring complex static and dynamic motion object features in the video. In addition, we propose a simple and effective adjacent frame difference loss called AFD loss to constrain the motion consistency of the video sequence. Video anomaly detection is a very important research problem in the field of computer vision. The aim of video anomaly detection is to automatically detect video frames where abnormal events occur in the video. Since the anomaly sample is sparse, the unsupervised or semi-supervised learning is the most commonly used method for video anomaly detection. Video frame reconstruction or prediction based on autoencoder is the most representative method among them. For the reconstruction-based approaches, due to the simple task of reconstructing input frames, where autoencoder only memorizes low-level details rather than understanding high-level semantics. For the prediction-based approaches, due to the appearance and motion variations of adjacent frames being minimal, the predictor can predict the future frame better based on the past few frames, even for anomalous samples. The inherent lack of capability of these two modeling paradigms in mining higher-level visual features and comprehensive temporal context relationships limits their further performance improvement. Faced with these limitations, our motivation emerges, under the semi-supervised learning route, how to design a better way to mine the complex temporal and spatial relationships in videos to establish more discriminative normal behavior patterns? Inspired by video codec theory, we propose a brand new video anomaly detection paradigm, video event restoration, based on keyframes for video anomaly detection. In the video codec, three types of frames are utilized, namely I-frame, P-frame, and B-frame. Based on these three types of frames containing explicit appearance and motion relative relationships, the video can be decoded. Inspired by this process, our idea sprang up, but should be also theoretically feasible if we give keyframes that contain only implicit relative relations between appearance and motion, and then encourage DNN to explore and mine the potential spatiotemporal variation relationships therein to infer the missing multiple frames for video event restoration. To implement the keyframe-based video restoration task, we propose a novel U-shaped Swin transformer network with dual skip connections called UST&DSC for video event restoration based on keyframes. The figure illustrates the overall framework of UST&DSC. UST&DSC follows the UNet architecture design, which consists of four parts: a feature extractor, an encoder, a decoder, and an output head. In addition, to cope with the complex motion patterns in the video so as to better restore the video event, we build dual skip connections in UST&DSC. Specifically, we introduce a cross-attention and a temporal upsampling residual skip connection to further assist in restoring complex dynamic and static motion object features in the video. Next, I will introduce each module in detail. First, the encoder of UST&DSC mainly consists of stacked multiple Swin transformer called SC encoder blocks followed by a convolutional layer. The detailed structure of the SC encoder block is shown in the figure. In order to learn long-range spatiotemporal dependencies, we calculate the local window attention by combining all the windows on the space corresponding to the current windows simultaneously. The outputs of such SC blocks are downsampled by a convolutional layer with a stride of 2, serving as the input of the next encoder stage. Symmetrically with the encoder part, the decoder of the UST&DSC also consists of 4 stages, each of which in turn is followed by a SC decoder block with a deconvolution layer for upsampling. The detailed structure of the SC decoder block is shown in the figure. We restore the missing frames in the decoding phase mainly by means of the conversion of the features from the keyframes extracted from the encoder part. For loss function, first, we use the Charbonnier loss to compute the RGB differences between the corresponding output frame and the real frame for appearance constraint. Then, we use the proposed AFD loss to ensure that the restored video sequence has the consistency of temporal variation with the real video sequence. Next, we present the results of the experiment. In this table, we compare the performance of our method with that of the state-of-the-art methods. It can be seen from table that the performance of our method on PED2 and Avenue datasets achieves state-of-the-art compared to other methods and has a substantial improvement over the pioneer methods based on the deep learning reconstruction and prediction paradigms. For the Shanghai Tech dataset, the performance of our method does not achieve the optimum, but it is quite competitive compared with other methods. Then, we present the qualitative results. There are some examples of video events restoration on 3 datasets. It can be observed that for the normal regions in the video frames, our method is able to restore them well, while drastic errors occur for abnormal event regions. This figure shows the results of video frames restored by our method compared with the output of existing reconstruction-based and prediction-based methods. It can be seen that the frame of the anomalous samples restored by our method have much large distortion and deformation errors in the anomalous region compared to the output of the previous two methods. This slide shows the anomaly score curves of some video clips on the three datasets. Obviously, there is a sharp jump in the anomaly score with the occurrence of anomalous events, and the anomaly curve returns to flat when the anomalous events disappear. Next, we first perform an analysis of the role of dual skip connections. As we can see from table, the encoder-decoder network without any skip connection, its performance is quite unsatisfactory. When adding these two skip connections in turn, the performance of our method is significantly improved. In order to feel the role of these two branches more intuitively, we visualized the transmission features corresponding to the two skip connections. First, this slide visualizes the attention maps of cross-attention connection on some samples. It can be observed from the figure that the cross-attention connection is mainly responsible for the transfer and transformation of dynamic objects features in the foreground. Further, we visualize the feature maps of the temporal upsampling residual connection in this slide, and it is obvious that this skip connection mainly serves the feature transfer and transformation of the background static objects. In addition, we can find that the cross-attention connection and the temporal upsampling residual connection in different decoding stages are responsible for different foreground and background parts, which complement each other well. Next, we analyze the impact of the AFD loss. The top table shows the performance differences on three datasets with and without AFD loss. It can be seen that the AFD loss has a performance boost on all three datasets, especially for the Shanghai Tech dataset, where it improves the AUC by 2.3%. And then, the bottom table is an analysis of the depth N of the SC block. We can find that the performance of USD-NDSC on all three datasets gradually improves as N increases. Interestingly, for the PED2 dataset, the performance improvement from increasing N is quite slight, while the improvement is very obvious for the Avenue and Shanghai Tech datasets. This can be explained by the fact that the scenes in the PED2 dataset are fixed and the motion patterns are relatively simple, so a shallow network can meet the modeling requirements. For the Avenue and Shanghai Tech datasets, their scenes are more complex and diverse, and place higher demands on the modeling capabilities of the network. Finally, let's make a summary of this work. In this paper, we introduce a brand new video anomaly detection paradigm that is to restore a video event based on keyframes. To this end, we propose a novel model called USD-NDSC for video events restoration, where a cross-attention and a temporal upsampling residual skip connection are introduced to further assist in restoring complex dynamic and static motion object features in the video. In addition, we introduced a temporal loss function based on the pixel difference of adjacent frames to constrain the motion consistency of the video sequence. Extensive experiments on three benchmark datasets show that our method outperforms most existing state-of-the-art methods, demonstrating the effectiveness of our method. This concludes our presentation. Thanks for your attention.